This video is about temperature and potential energy in matter. So first off, kinetic energy. Kinetic energy is the energy of motion, which is related to both the mass and speed of something. Now, temperature is a measure of the average kinetic energy of particles in a substance. Since when you have a substance, the mass of its particles are not changing, when we change something's temperature, we are therefore changing the average speed of its particles. So we're mostly going to talk about temperature in terms of motion of particles. Now, it's important to note that when you increase something's temperature, not every particle in the substance immediately starts going faster by the exact same amount, but on average, they start to move faster. The important units of temperature for this course are degrees Celsius, which most people are familiar with, and kelvins, which is also referred to as absolute temperature. Now, the Celsius scale, which most people know and are quite familiar with, is based on a couple of important temperatures for water, with 0 degrees Celsius being the freezing point of water and 100 degrees Celsius being the boiling point of water at normal pressure. And so that's really where the degree Celsius comes from. You mark those two temperatures on your thermometer, and then you divide up the space in between by 100 even gradations. And so that's where a degree Celsius comes from. It's 1/100th of the difference between the boiling and freezing points of water. Okay, well, the Kelvin scale has that same idea, or the same size unit. So in Kelvin, 0 degrees Celsius is equal to 273 Kelvin. Notice it's not a degree Kelvin, it's just a Kelvin, and it's a capital K because it's somebody's name. And 100 degrees Celsius is 373 Kelvin. So you'll notice that the change between freezing and boiling is actually exactly the same. In both instances, the difference between the freezing and boiling point ends up being 100. So the delta T here is 100 degrees Celsius, and the delta T here is 100 Kelvin. So 1 Kelvin is actually the exact same size as a degree Celsius, and it was invented that way on purpose. Everyone was familiar with the degree Celsius, so we want to keep the same size unit. That makes converting easier. What Kelvin does, though, is it takes away negative temperatures. And while we're all familiar with negative temperatures and they work fine for day-to-day life, when we're doing calculations, and if we're thinking about temperature as a measurement of average kinetic energy, how can a particle have negative kinetic energy? How can it have a negative amount of energy? If it's moving, then it has some amount of positive kinetic energy. So those negative temperatures don't really make sense when we think about what temperature actually means. So what Kelvin does is it gets rid of negative temperatures. And so the coldest possible temperature, which is called absolute zero, is just about negative 273 degrees Celsius. I think it's really 273.15, but hey, close enough. So with Kelvin, they basically said, if that's the coldest temperature, then let's call that zero. And at absolute zero, that's when all motion in the particles stops. And that, therefore, having a value of 0 makes a lot of sense. Your average kinetic energy at that point is 0. There's no motion. Therefore, the temperature should be 0. So absolute 0 is 0 Kelvin and minus 273 Celsius. And from that point on, every change is the same. The degree Celsius is the same as 1 Kelvin. So they're always 273 off from each other. Now, you've noticed already that when we change temperature, it doesn't matter which unit we use, if we use degrees Celsius or Kelvin. A change from 20 up to 52 degrees Celsius is a delta T of 32 Celsius, positive. The change in temperature for Kelvin is also 32 Kelvin. And if you don't believe me, you can add 273 to both, and you get 293 Kelvin. And then what do you get? 325, and if you subtract these two, then you should get 32 Kelvin. So obviously if you add 273 to both, then it won't change the difference. So when you do changes in temperature, sometimes you'll see in the data booklet that it says delta T and it lists the units as kelvins. You can also use degrees Celsius if you are doing anything with a change in temperature. But when we do calculations, and especially as we move into what are called the gas laws, and we talk about gases, it's really important that we're using kelvins. And here are some examples. In some gas law questions, they're going to talk about doubling or halving the temperature. So they're talking about doubling or halving the average kinetic energy of something. You can't do that in Celsius because of the negative possibility of the Celsius, but also because its reference point isn't 0. So for example, if I take 27 degrees Celsius and I want to double it, the answer is not 54 degrees Celsius, because you've doubled the Celsius value, but you haven't actually doubled the Kelvin value. So the first thing you need to do is add 273 to the Celsius. So 27 degrees Celsius is 300 Kelvin. And now you can double it. And so doubling the temperature is actually going from 300 to 600. So we've increased the temperature by 300 kelvins, which is also increasing the temperature by 300 degrees Celsius. So this is equal to 327 degrees Celsius. If I want to convert back into Celsius, I subtract 273. Okay, same idea here. If I want to know what half that temperature is, I first have to turn it into Kelvin. Then I half it. So this was 2 times. This was times a half. Now I'm at I can write. Now I'm at 150 Kelvin. And now I have to subtract 273 to turn it back into a Celsius value. So now I'm going to see that it's negative, and it's negative 123 degrees Celsius. So that's actually something with half the energy, half the kinetic energy on average. So that's temperature, that's Celsius, and that's Kelvin. Okay, what about potential energy? So potential energy is stored energy. It's a fairly abstract concept to try to wrap your head around, but it's not energy that you can sort of experience. It's stored up, and then maybe later it gets released, and you can experience that when the energy is released as something getting warmer. Maybe it's released as heat energy or light energy, but the actual potential energy is stored up, and so you can't really measure it directly or really experience it directly. So it's stored energy that can be released at some point in time. And in chemistry, we often refer to potential energy as enthalpy, and it gets a symbol H, which I realize is kind of confusing, but we're going to have to deal with it. So I will both refer to potential energy, but also enthalpy throughout the course. Okay, so enthalpy change. The total chemical potential energy of substances can't be measured, but we can measure how the enthalpy is changing given how it's interacting with the surroundings and given how the temperature of the surroundings is changing. Okay, so endothermic changes and exothermic changes. An endothermic change is when a process absorbs energy from the surroundings, and therefore, where does that energy go? It goes to the potential energy of the system, whatever system we're looking at, whether it's a chemical change or a physical change. So in an endothermic process, you have heat energy transferring from the surroundings into our system, so into our chemicals usually, into our particles. And so that means that the particles are gaining potential energy, but it's at the expense of the energy of the surroundings. So the surroundings lose energy. And so usually we think that endothermic processes end up feeling cold. So if there's an endothermic chemical reaction happening in a beaker and you touch it, it will feel cold because it's absorbing heat out of your hands and pulling it into its potential energy. So even though it absorbs energy, it doesn't get warm. It's absorbing the energy and it's converting that energy away from heat and temperature into this enthalpy, into this potential energy. Endothermic processes involve particles separating as their attractions are broken apart by this absorbed energy. And so generally it makes things less stable as they get pulled apart from one another. Exothermic changes involve the opposite transfer of energy. So whatever process, whether it's chemical or physical change is happening, ends up releasing some of its stored energy. Usually that energy gets released as heat energy. And so if you and I are near this process, we're part of the surroundings, and we're going to experience that heat energy being released to us. And so it's going to make us warmer. It's going to make our temperature go up because we are gaining that energy, so we feel warm. But the particles of the system are losing the energy, they're releasing the energy, and therefore they're losing their enthalpy, so they have a negative enthalpy change. And so exothermic changes usually, or pretty much always, involve particles coming together and forming attractions with each other, and in doing so, they become more stable and they release energy in the process. So like when chemical bonds are formed, the atoms come together, the bond is formed, and energy gets released to the surroundings. Whereas in the endothermic process, this would be like the breaking of chemical bonds requires energy input to separate the atoms apart, and so energy has to be absorbed to do that. Lastly, how does this apply to the states of matter? So you're probably familiar with solid, liquid, and gas, and for our purposes, we're not really going to be talking about plasma. So these are our three phases of matter, and you should be able to describe the relative motion of the particles, such as in solid, they're in fixed positions, but they are vibrating. In liquid, they are close together and moving past each other with slightly more space between the particles. And in gas, the particles are very far apart from one another. Now, the phase changes are from solid to liquid is melting, from liquid to gas is vaporization. Both evaporation and boiling are different kinds of vaporization. We can reverse those changes as condensation and freezing. And then there's the two that are trickier to remember. In some cases, solids do go directly to gas, and that's called sublimation. And gases can go directly to solid, that's called deposition. Now, if you think about the rule that I said back here, endothermic processes involve particles separating and attractions being broken. And so if you think about the phase changes, anything going in this direction involves particles separating. Solid to liquid, they move a little bit apart from one another. Liquid to gas, they move very far apart. Solid to gas, they move very far apart. So all of those changes, you're expected to know that those changes are endothermic changes. So when we do melting or vaporization or sublimation, the particles are gaining potential energy as they go into those changes. Whereas the reverse is true for the other phase changes. When gas is condensed down to liquid and they come together and form attractions, they end up releasing energy. And in order to freeze, liquids need to release energy to the surroundings to turn into solids. And for gases to deposit and undergo deposition, they also must release energy. So in the other direction here, we have changes that are exothermic. But as a general rule, what I want you to try to remember is that when particles come together, they release energy. That's an exothermic change. And when particles are separated, that requires energy input. So we're saying plus energy. You have to put energy into, endo is like into the system, instead of exit like exothermic. And we see this during phase changes where when we add heat to the system, adding energy to the system, you start off with a solid of something, and then as that solid melts, you actually see that its temperature plateaus, and the temperature does not change during melting. Now you're still adding heat to the system, so where is that heat going? It's during melting that we have the endothermic change. So this process here is just warming. We have the temperature is rising of the solid. That's not endothermic. It's just getting warmer. Then, as the solid turns into liquid, we have this endothermic melting process happening, where the energy we're adding is going into the potential energy of the particles. And that's why we don't see the kinetic energy going up. The temperature isn't going up. Then, once everything is liquid, we can warm up the liquid. So this is, again, just an increase in temp, adding energy. And then, when we start boiling, we should see during boiling that the temperature plateaus again. Well, we're still heating it, so where is all that energy going? That energy that we're adding is now going into the potential energy of the particles as they become gas. So phase changes are endo and exothermic. And the phase changes where we have to supply energy, like melting and boiling, those are endothermic changes. Heat has to go into our substance to get its particles to separate to cause the phase change. The reverse phase changes are here. If you have a gas and it cools, So this is just a gas cooling off. Then it will condense. So condensation during this time is an exothermic change. Heat has to be lost from the gas particles for them to become liquid. Then you can cool a liquid. And then during freezing, that's an exothermic change as well. The liquid particles have to lose heat to the surroundings, such as like the freezer. And during that time, the temperature doesn't change, but they lose their potential energy. And then we get a solid that can become cooler.